So moving on to 5.1, we're going to be talking today about magnetic fields, how it's related to current carrying wires, and also moving charges. If you haven't completed the reading, please go to the Coletta textbook, chapters 21 and 22, and please start your homework. This should be homework 6 in Sapling, if you're in 112, which will be magnetism, and also homework 8 and in Physics 131. Also, labs 11 and 12. In the last chapter, we talked a lot about how magnetic fields are caused by unpaired magnetic dipoles, unpaired electrons, and they're spinning and moving, and they're those spins actually do create a magnetic field, and how a group of them all spinning in the same direction and moving in the same direction will create a magnetic field pointed in that same direction. Well, we also were talking about the Earth, right? And so at the center of the Earth, you have probably these huge, molten metal that's all spinning and turning, and that those unpaired electrons are moving to the right. Well, that creates a current pointed to the left, and so these moving electrons that are creating a current will actually create a magnetic field, right? So what we found out later on is that a current itself will create a magnetic field. And we've used currents and magnets to employ creating energy from generators. You have a water wheel. It spins magnets, and if you put the magnets inside a coil of wire, well, that will create an interaction, which will then create a voltage, right? So, and we've also used this in high energy trains, right? You have a train that has these little magnets on it, right? Little magnets holding it up. Well, in the track is a current carrying wire, and they then repel each other if they're pointed in certain directions, and it makes the train actually float and actually can make it move as well. So we've employed this concept that current is a magnetic field too, and use it to generate power as well as to make things move. Well, let's talk about how current does create a magnetic field. So here is a current carrying wire pointed out of the page. So I'm going to mark up the document. So you have a current carrying wire pointed out of the page. So just imagine this is a wire pointed straight up, and its current is pointed up. Well, notice the iron filings that we talked about last time are creating a circular pattern, right, around this current, which is kind of odd, right? I would think if the current is pointed one way, that the magnetic field might be pointing along that same direction. But what's interesting is that this magnetic field is actually going around the current carrying wire, right? Here's another picture too. This is a little bit different. It's, it's got a blue background, and you could see it's actually probably a better three-dimensional picture than this one. But you see the same pattern. You see this circular pattern. Okay. And I just gave the current a direction. I don't know I can't see from the iron filings which way the magnetic field is pointed as far as left or right. But if you placed a compass here, well, now that compass needle, whatever direction it would be pointed, would indicate the direction of the magnetic field at this distance out from here. And so what we're going to find out later on is if the compass needle is pointed to the right, which means that's the north end, it's the south end. And that would be related to a current pointed out of the page here. These are the magnetic field lines in blue. So these are the magnetic field lines in blue. Notice that they're counterclockwise. Well, this X refers to into the page. And a dot will refer to out of the page. Right? So that X, where the wire is, means the current is into the page. So when the current is into the page, you get this clockwise pointed magnetic field. Pretty cool. So we could create a relationship of the direction of the magnetic field to the direction of the current. Now that we know the magnetic field is pointed in a circular pattern around a around a current carrying wire. So this is actually a really cool connection between electricity and magnetism, right? A magnetic field will form a pattern which is circular around this, right? And if you place little compasses around this current carrying wire, it's going to tell you the direction of the magnetic field. Well, the cool thing is when you flip the current in another direction, those little compasses are going to actually change in the direction that they're pointed. So there is a direct relationship between the direction of the magnetic field and actually electricity, right? So let's just draw it right here. Let's say this is pointed straight up. Let's say the current is pointed straight up, right? And what that means is the electric field is going to be pointed straight up too, if the current is pointed straight up. Okay? Well, notice at this point that if the electric field is pointed straight up, the magnetic field seems to be at a 90-degree angle to that. It looks like notice that this angle between this piece of paper and this is 90 degrees, right? So there is a cross product relationship between the electric field and the magnetic field. Okay? And that relationship is related to the what that intermediary is the moving electrons. So like I had talked about, if you have a current pointed up, so it'd be pointed straight up, notice that the magnetic field is going to be moving in a counterclockwise fashion, right? Correct? And that if the current is pointed down, so this is counterclockwise magnetic field, right? Well, if the current is pointed down, if the current is pointed down, whoops, I don't want to draw. If the current is pointed down, notice that this is clockwise. This is a clockwise magnetic field. Okay? Well, let me try to illustrate this a little bit better. Okay, so I'm going to go to, I actually clicked on this Magnet Academy link, and that brought me to here. Okay, so here is a wire. It's a current carrying wire. Okay, notice the electrons are moving up. Okay, it's a current carrying wire. The electrons are moving upwards. And that means the current would be pointed down, correct? Remember, current, we learned from circuits that current, the direction that the current is pointed is opposite the direction of the flowing electrons, okay? So the electrons are flowing up, but the current is pointed down. And what we had learned that when the current is pointed down, the compass needle will be pointed, and this is the red is north, blue is south. The compass needle is going to be clockwise around it. Okay? The compass needle is going to be pointed clockwise. Right? If we reverse that direction, now the electrons are flowing down and the current is pointed up. Well, now notice that the magnetic field is pointed opposite that direction. Okay? So the magnetic field in this case is going to be counterclockwise. Okay? The closer you are, the stronger the magnetic field. The further away, the weaker the magnetic field. Okay? So this link is a really cool link to kind of, illustrate the relationship between current and thus the electric field. The electric field would be pointed up in this case, and the current would be pointed up. The electrons are moving opposite the direction of that. And also the 90-degree angle, which is this plane right here, to the magnetic field. And that magnetic field is around that current carrying wire. Well, we could actually make a rule for this. This is actually called the right-hand rule, which we'll talk about in a second. But we could make this this relationship in a second. But what's really neat is that these moving charges, what's happening is these electrons in the simulation are moving, right? And so by those electrons moving, they're actually creating, electrons themselves, whether they're moving or not, are going to create an electric field. But now that they're moving, they're also going to create a magnetic field on top of that, right? So moving charges create both a B field and not, they will always, on top of their already created electric fields. So electric fields are created whether they're moving or not. Right? We know that a stationary electron is going to have that electric field. But so an electron or a proton will always have its electric field. But once it begins to move, now it creates a B field on top of that. Okay? So now we could actually make a relationship to a moving charge to an electric to a magnetic field. Okay, but before we do that, let's kind of make sure that we understand how to look at the relationship between the direction of motion of that charge and also the direction of the magnetic field. So this is called the right-hand rule, right? So what you're supposed to do is you're supposed to imagine that you're grabbing the wire just like this, and you curl your fingers around in the direction that the wire is pointed, right? So notice that this person's hand is pointed right there, and their fingers are making a counterclockwise rotation. So their thumb is pointing in the direction of the current. So the thumb is pointing in the direction of the current. Their fingers are wrapping around in the direction of the magnetic field. So if you look at it right here, and that magnetic field is little tangent lines around that. At this point, it would be pointed to the right. Here, it'd be pointed in, towards the top of the piece of paper there. Over here, it'd be pointed to the left. And so what you get is this relationship between current at a 90-degree angle to the magnetic field. And the magnetic field, if your thumb is pointed upwards, your finger is going to wrap around that wire in a counterclockwise direction. Okay? So let's practice this. Let's do a relationship between a moving charge and the direction of the magnetic field. So what I want you to do is we're going to just do the top pane right now. You have a positive charge moving to the right, and I want you to apply the right-hand rule and try to figure out what the direction of the magnetic field is at each one of these points, A, D, C, and B. And you're going to want to classify them as up, or positive Y, down is negative Y, to the right is positive X, to the left is negative X. They could also be out of the page, right? So this is a three-dimensional figure that we have to think about. Oops, I should draw that a little bit more straight. So we have to think about a three-dimensional figure now, because that cross product can take on 3 dimensions. So this is going to be positive Y, which is up. Down is going to be negative Y, as always. To the right is going to be positive X. To the left is going to be negative X. But now we have this in and out of the page business. Out of the page is positive Z, right? X, Y, and Z. And that's out of the page. And into the page, I should put vector heads on these guys. Into the page is going to be negative Z, or into the page. So you're going to have to classify A, B, C, and D as any one of those directions. And let's see you apply your right-hand rule. Now you have to really be careful. This is called the right-hand rule. You must use your right hand. So you're going to point your thumb in the direction of the current, or also the direction that the positive particle is moving. All right? And try to go ahead and pause the video and just try this top one and figure out what the direction of the magnetic field is at each one of these points. Pause it now, please. All right, let's try it out. So if I point my thumb in the direction that this positive particle is moving, my thumb would be pointed to the left of my screen. And I'm curling my fingers, and they seem to be above it. They seem to be going into the page. So my fingers are going into the page, which is negative Z, right there. And if I let this is going to be now, so the magnetic field is rotating around this, up into the page there, down on the other side of this, and this is actually in D. When I bring my fingers around, they seem to be kind of coming out at the bottom of this, out of the page, which is going to be, so this top part was negative Z, this bottom part is going to be positive Z. Okay? Now, I have to keep my thumb pointed to the right, and I can't curve my hands up or down, right? So what you find out, that in front, this actually has no magnetic field, and this also has no B field as well, right? Because that's to the left. The magnetic field has to make these little rings around the object, right? These little counterclockwise rings. So I'm imagining this particle is moving this direction. This positive particle is moving to the right. And that's the direction, it's moving to the left. So it's got a negative Y direction velocity. Okay, and so the magnetic field is pointed either into the page or out of the page. A and C are on the line of this positive particle, so directly on that axis there is going to be no magnetic field. Okay? Well, that's a positive particle, and the rule for the right-hand rule is that your thumb needs to point in the direction that the current is flowing, or that a positive particle is moving, right? Well, now we have another example where you have a negative particle that is moving out of the page. So what do you do when you have a negative particle? Well, you either point your thumb in the direction that the negative particle is moving and do the opposite of whatever your fingers tell you, or you imagine the direction that the current is, right? So if electrons are flowing to the left, for example, if electrons have a velocity to the left, the current is going to be pointed to the right. And by the way, that's also the direction that a positive particle is going to be moving. Come on. I'm going to erase this, try to draw this a little bit better. So if you have a negative particle that is moving to the left, then the positive particle is going to be moving to the right. And the current is also going to be pointed to the right. So in this next example, just be aware that this negative particle is directed out of the page. So the right-hand rule means your thumb has to point in the direction of the current or a positive particle. So whatever that velocity is given, you have to do the opposite. So what I am going to do here is I'm going to point my thumb into the page, because that's the direction of the positive particle or the current, and then answer the question like that. So go ahead and pause the video now and see if you can answer the directions of the magnetic fields at A, B, C, and D. Pause it now, please. All right. Well, again, the electrons are flowing out of the page, right? But your thumb should be pointed into the page, which means if I do that, that means the magnetic field is going to be circular around this axis right here. It's going to be circular around this axis. And when I'm pointing my thumb into the page, it looks like it's making a clockwise pointed magnetic field. Okay, so the current is going in the negative z direction because the electrons are flowing out of the page. So in this case, the magnetic field is going to be pointed in a clockwise fashion. That means B is going to be to the right. A magnetic field is going to be pointed to the right. A is going to be pointed up. C should be pointed down, right? And D is going to be pointed to the left. Okay? So that's how you kind of use the right-hand rule to determine the direction of the magnetic fields around positive direction and positive and negative particles, but also in different directions too. So I wanted to give you a nice little practice to test that. That brings us to the Biot-Savart law. So how do you quantify that? Once you've figured out how to make the connection between the direction of the magnetic field and the direction of the particle, how do you quantify that? Okay. Well, this is called the Biot-Savart law, right? And that is given by mu naught over 4 pi times QV sine of theta over r squared. And the reason why this is sine of theta right here is that the direction that a particle is moving, okay, so let's say a positive particle is going to be flowing out of the page. So you got a positive particle moving out of the page, right, at this point. Okay, so if it's pointed out of the page, and you want to know the direction of the magnetic field over here, just to its right, well, that magnetic field is going to be pointed up, correct? And so they're making a 90-degree angle to each other, right? So that's why this is actually QV sine of theta, okay? So we'll talk about what mu naught and 4 pi is in a second. But the particle, the direction of the particle, the velocity of the particle, sine of the theta is going to account for that 90-degree angle here. Now, this is kind of, if you've noticed, the electric field of a particle moving, the electric field is just going to be kq over r squared, right? So that's the electric field of a particle, right? And we had an absolute value, and there is an absolute value around this as well, okay? But this k is kind of similar to this. This mu naught over 4 pi is a constant. In fact, that mu naught is actually 4 pi times 10 to the negative 7th, right? And that's the unit of measurement of a magnetic field is a Tesla, right? Okay, and that Tesla is the unit of magnetic field. The charge here, Q, its charge is a Coulomb, and velocity is meters per second. So what's really cool is that all of this stuff is actually related to an amp, right? So charge is moving over a period of time. So what we have here is a relationship which is very similar for a magnetic field that is very similar to an electric field, right? Both of them are over a distance apart squared, right? So this is the distance r. So here's our velocity of our proton. Here's where our little proton is, right here. And it's moving out of the page, okay? And this is the distance r from here to here, okay? And so that strength of that magnetic field that is pointed up here, and we found that direction by using the right-hand rule, the strength of that is related to the amount of charge times its velocity times the sine of theta to account for that angle, right? If it is pointed at some weird direction like that, if that velocity is pointed in a direction like that, only the component over here that is at a 90-degree angle, all right, only that that component is going to be related to the magnetic field, okay? Okay. So, and this mu naught over 4 pi, well, mu naught is called the permittivity of free space. It's a constant, so it's actually 4 pi itself. What it does is it makes this equal to 1 times 10 to the negative 7th, right? This whole thing, 4 pi over times 10 to the negative 7th, is actually just going to be 4 pi divided by 4 pi times 10 to the negative 7th, right? So what it does is it reduces the size of this magnetic field, right? So you find out that that constant drops out when you graph the magnetic field versus QV. So if we graphed, how they found that constant is if you graph magnetic field versus QV sine of theta divided by r squared, what you get is this. You get like a slope right here, and that slope is going to be 1 times 10 to the negative 7th. Okay? So it's a really small slope, but it's actually 4 pi times 10 to the negative 7th over 4 pi. Okay, so the Biot-Savart law is a relationship between a moving charge and the magnetic field, and it takes on the same kind of structure as an electric field. Well, let's go ahead and do a problem, okay? So let's apply the Biot-Savart law, right? So here we go. We have a proton, okay, and the charge of a proton is going to be, what is that? From what I remember is 1.6 times 10 to the negative 19th coulombs, and that's the charge of a proton. And that looks like it's moving along the positive x axis. So it's a positive x-axis. So it's moving to the right. The z-axis is pointed kind of in this direction, and the y is here. And they want to know what the magnetic field, so it's at the origin right now. They want to know what the magnetic field is at this position, right here. So when it's at a distance x equals to 1 millimeter, 0 y direction, and 0 z direction. So that position 1 is this. This is position 1. They also want to know what the magnitude and direction of the B field at a point right above the particle at position 2. So this is position 2. And then finally, they want to know what the magnitude and direction of the B field is at a position over here at position 3, which is 1 millimeter to the right, 1 millimeter up. Okay? Well, if you recall from something that we've done earlier, is that I asked you what the, so this is similar to this, right? Correct? So we noted that at position A, since that is along the axis, and that is not in, it doesn't deviate in the y direction from this particle, which is moving in the negative x direction, right? So what we found out that was 0. So I'm going to guess that the B field at this point right here is going to be 0 at position 1. Okay? And I want to figure out the direction of the B field over here. So the B field at position 1 is going to be 0. So there is going to be no direction to that. The B field at 2. Well, now I'm going to point my thumb in the direction that the positive particle is moving, so I'm going to be pointing it up in the positive x-axis. So my thumb is pointing that direction. I'm having my fingers curl around, so my fingers are curling around, and it looks like this thing is going to be pointed. So the B field at 2 is going to be pointed to the right. Well, sort of in the positive z direction, I should say. And this is kind of weird, but this guy is also pointed in that direction too, except it's the x direction component which is not going to be helpful to it, right? So this, so for position 3, this is not going to help it, right? That's going to be unimportant. It's the fact that it deviates from the y-axis is what's going to allow it to have a B field. But since it's so far away, right, it's this distance away, which is 1 millimeter up and 1 millimeter to the right. So that distance there is going to be a distance r, which is going to be equal to, well, I'm going to just say r squared is equal to 1 millimeter, which is 0.001 meters. That you're going to square that, plus 0.001 meters that you're going to square that. This distance right here for position 2 is just going to give you, and I'll denote this as R3. Position 2 is just going to be, and if I square that, just to be consistent, 0.001 meters, then I'm going to square that whole thing. That's that distance up, right? It's just actually just R2, but I'm putting it into a format. I probably shouldn't do that. That might be confusing. That distance R2 and I'm going to erase this and erase this. I'm going to go back to this real quick. That R3 is the square root of these guys, right? That distance from here to B3 is R3. R2 is just 0.001 meters away, right here. Okay? So what I'm trying to do is I'm trying to think about the direction of the B field, but also the strength of the B field. So I made B3 equal to as a smaller vector. So it's just a little guy, right? While B2 is going to be a really strong vector pointed in the positive z direction. So the y component is going to give both of these, the y distance is going to give both of these, is what's responsible for the B field, right? We can see the x direction isn't contributing to the B field because that is along the direction that the particle is moving. So let's try it out. So overall, let's do this. Let's go ahead and take a look at the B field at position 1. And let's just confirm that the B field at position 1 is going to be equal to 0, as we suspect. Okay? So I'm going to go ahead and mark up this document. And I'm going to, so again, we've determined that we're just confirming that B1 is going to be 0. So this is going to be mu naught over 4 pi, right? And that's kind of like that's a constant. And we're going to have Q, which is 1.6 times 10 to the negative 19th coulombs. And the speed that it was given, what was our speed? Our speed is 1 times 10 to the 7th meters per second. And it's a distance 0.001 meters away, but you're squaring that because that's R1 squared. So that's 0.001 meters away. It's 1 millimeter, right? Well, you're going to be multiplying this by the sine of theta, but the sine of theta, right, in this case, is going to be 0, right? So this is 0 degrees, which means this is going to be 0, and that's going to make this whole thing 0. So just for the fact that this sine of theta, right, since that guy is in the line of that is what's going to make that this angle here 0. Okay. Interesting. So it is in fact 0 Tesla, that B field. Okay. Let's try position 2. Position 2, this angle between the velocity vector and position 2 and the distance, right, that angle is actually 90 degrees. So we're going to have the same setup as above, got mu naught over 4 pi, and it's got the same charge, 19th coulombs, and it's got the same velocity, which is 1 times 10 to the negative 7th meters per second. But, and it's got actually the same distance as well. You got to make sure you square it. But this sine is going to be 90 degrees, right? So that just goes to 1. So when you work this all out, well, mu naught is 4 pi times 10 to the negative 7th, right, divided by 4 pi. So this part goes to 1. So that's just 1 times 10 to the negative 7th. And that's Tesla meter per amps. Okay. And you're going to multiply that by 1.6 times 10 to the, by all the rest of this, I should say. So I guess what I'm saying is this whole thing works out to be, so this is 1.6 times 10 to the negative 7th times 10 to the negative 19th times 10 to the negative 7th, 10 to the positive 7th, I should say. So that's, what is it? Negative 7 plus 7, so that's 10 to the negative 19th. So I guess this is going to be 1.6 times 10 to the negative 19th, but this on the bottom is going to be 10 to the negative 3rd that you're squaring, so that's just 10 to the negative 6th. So I guess what's going to happen is this whole thing is going to work out to be 10 to the negative 13th Tesla. And that's going to be pointed in the positive z direction. It's going to be pointed perfectly in the positive z direction. Cool. Cool. Well, if you work out position 3 using the same thing, there's a couple ways to work it out, but let's work out position 3. So the B field at 3, and let's set that up, okay? And we have to remember that position 3, so position 3 is over here. That makes an angle of 45 degrees to that point, okay? And that's going to be important, okay? So that position 3 was making an angle of 45 degrees, okay? B3 is making an angle of 45 degrees to the direction that the object is moving, right? So again, you're going to have mu naught over 4 pi, okay? And again, we're going to have the same setup, 1.6 times 10 to the negative 19th coulombs, and that object is moving at 1 times 10 to the 7th meters per second, which is extremely fast. But again, it was a distance R3, which is 0.001 meters squared plus 0.01 meters square root. So basically, that's going to be equal to 0.001 meters squared plus 0.001 meters squared away. But that sine of theta is going to be 45 degrees. Okay. So we have to take that into account. So not only is it further away, but it's at an angle, which is going to lower the strength even more. Okay. And I think it looks like what they've already computed here, that works out to be 0.57 times 10 to the negative 13th Tesla in the positive z direction as well. So that's how you have to compute it. You have to not only take into account the distance that it is, but also the angle of that data point where you're going to place the sensor to where the velocity is moving, right? So basically, you have to take into account that cross product, which is going to be the upper portion of that. Okay? So the angle between the B field and velocity. Okay? So that's how you deal with the Biot-Savart law with a moving particle. Well, there's an application of this, but to a current carrying wire. Okay? So if this part right here, so this is actually more of an offshoot of Ampere's law, but this is mu naught. Again, you have mu naught over here, but now it's going to be divided by 2 pi if you have a current carrying wire. And we'll get in, if you're in the calculus, version, we're going to actually have to derive this stuff. But if you think about it, this 2 pi d is almost like a circumference. Well, it is a circumference, right? And where this is the distance d out, and this is the current carrying wire, right? So this is the current carrying wire, and here's the data point, and it's going to be pointed into the page. So that means the magnetic field is going to be, and I'm going to say I is going in that direction. So here we have a dot. Okay, so now we're getting into current carrying wires, and this is going to be going down at this point, just to the right. At this point, just underneath the wire, it's going to be to the left. At the top of the wire, it'll be to the right. Okay, so the B field is going to be pointing in circles around that, and since it is a circle and that is a circumference, well, that's why you have the 2 pi d on the bottom. And there is no cross product stuff. Again, you're going to have to use the right-hand rule to figure out the direction of the magnetic field at each one of those points. But since we're dealing with current, you don't have to do what you're doing up here and do cross product of the direction of the magnetic field and the direction that the particle is moving. Okay? And you probably also noticed that this is just 2 pi d at the bottom. It's not an r squared, right? So that gets kind of taken care of when we're actually doing this here. So let's take a look at a current carrying wire. And let's take a look at the direction of the magnetic field around a current carrying wire. And here it's going to be showing a current into the page. So that means I'm pointing my thumb into my screen right now, and my fingers are kind of curling around in this direction. So this is going to be a clockwise magnetic field. So that last thing, this was the distance d out. Again, notice that this is a circumference, right? So that magnetic field is, so the magnetic field at this point right here, the distance d away, is going to be equal to the strength of the current over 2 pi times that distance, right? And it should be pointed straight down. And that's, you know, an application of the Biot-Savart law. It's actually derived from Ampere's law. Okay? Oh, and so this is what it looks like if we show it from that upward perspective, right? So if you imagine this is a blue wire, okay, notice that the magnetic field is counterclockwise. I mean, it's clockwise around that. If the field, if the current is out of the page, it's going to be going counterclockwise. If the current is into the page, it's going to be clockwise, right? And if you had two wires, well, it would be right in between. The magnetic field would be pointing straight up. So it's kind of cool. So again, you have to remember that X means out of the page. If we're referring to current, then the current would be out of the page. Or if we're referring to the magnetic field, the vectors are into the page. Basically, X is a vector into the page. A dot is a vector out of the page. So if you see a wire, which is usually a little circle with a dot in it or an X in it, that's referring to the current. If you see a series of X's or dots, those are probably the magnetic field. Okay? So let's practice this on this tutorial. So now we're going to actually do right-hand rules applied to current carrying wires, and we're going to practice that. Okay, so let's do the left-hand wire pane first. You have a current carrying wire, and it looks like the current is pointed into the page because you have a little X there. And we want to know what the magnetic directions of the magnetic fields are at A, B, C, D, and E. Applying the right-hand rule, so you're going to point your thumb in the direction of the current, and you're going to curl your fingers in the direction of those, and your fingers will represent the direction of the magnetic field. So go ahead and qualify those magnetic directions of the magnetic fields at each one of these points. So pause the video now and try it. Okay, so I'm pointing my thumb into the page. And when I point my thumb into the page and I'm curling my fingers, it looks like, it starts to feel like my fingers are going to be pointed kind of counterclockwise-ish. I mean clockwise-ish. So clockwise. That means at this point, the magnetic field is going to be pointed up. At B, it's going to be pointed to the right. At C, it's going to be pointed down and to the right. At E, it should be pointed straight down. And at D, it should be pointed up and to the left. So just kind of like little tangents along a circle. That's how I'm thinking of the magnetic field at each one of these points. Okay? How'd you do on that? Well, let's try one that's a little bit more difficult. And you're going to have to do, your fingers are going to have to curl in 3 dimensions. That means probably your fingers are going to be curling around the wire in 3 dimensions. So this one has a current that is pointed up. So you're supposed to get the direction of the magnetic field at A, which is at this top part, at C, at D. So A and C are just to the left of the wire. B and D are just to the right of the wire. So try to get the magnetic field to the left of the wire and right of the wire and assign the directions to the magnetic fields. So try the right-hand rule and pause the video and try this one right now. Okay, so when I curl so I'm pointing my thumb up, and it feels like my fingers are curling around the wire, and they're going to be curling in this direction. So it looks like my fingers are going into the page, and over here the B field is going to be out of the page. If the B field in between us and the wire is going to be just to the right, and on the other side of the wire it will be to the left. So what does that mean? Well, that means the B field everywhere over here on the left-hand side of the wire is going to be out of the page. And the B field over here is going to be into the page everywhere just to the right of the wire. So this is going to have a B field in, and this is also going to have a B field in, while A is going to have a B field out, and C is going to have a B field out. So everywhere on the left side of this wire is going to be an outward pointed B field. Anywhere on the right side of this wire is going to be an inward pointed magnetic field. All right. So there's a problem-solving strategy related to quantifying and doing quantifying and applying right-hand rule to magnetic field problems of a current carrying wire, or actually just of a moving particle too. So what you're supposed to do is draw a picture of what is going on and establish a coordinate system, okay? And you need to very succinctly, from your written description, is actually diagram out as much as you can. And so drawing the coordinate system, but also identifying the point at which you're going to be calculating and figuring out the direction of the magnetic field is. So that's kind of where you would place a magnetic field sensor. And that sensor would detect the magnitude of the magnetic field, but also the directions. And so that point P is going to be a distance d away from the wire or d away from the moving particle. Okay. So you have to remember, then you want to go ahead and figure out the direction of the magnetic field at this point. Okay, using the right-hand rule. Okay. So it's always going to be symmetric. If there's a magnetic field into the page, there will be a magnetic field out of the page. If it's to the right, there'll be another part which will be to the left. So the opposites will actually occur on either side of the wire or the moving particle. Okay. You could even draw some places where the magnetic fields are actually zero. Okay. Well, now you're going to have to go ahead and you're going to have to calculate it, right? So you have to make sure if there are any angles and you're calculating the magnetic field due to a moving particle, that you establish that sine of that angle is, because you have to deal with the sine of theta also. And you also, since it's going to be a three-dimensional coordinate system, your distances might be also in 3 dimensions as well. Well, actually, it'll be in 2 dimensions, right? So just like that earlier problem where we had, there was a x direction, right? There was a point up here, and we had to calculate, this was 1 millimeter to the right, and also 1 millimeter up. And you had to deal with that theta and everything like that. So you have to establish those distances, but you also have to take into account, if you have a moving particle, the sine of theta as well. Okay. With current carrying wires, it's actually a little bit easier. You just need to know what the current is, okay, and the distance to it. And then you'll use your right-hand rule to establish the direction of it. Well, let's try a problem, okay? And this is kind of like our tutorials that you're going to do in a little bit. But you're going to establish, what you want to do is establish the direction and magnitude of the magnetic fields at A, B, C, and D, given a 3I wire pointed into the page, and at this dot is a 2I wire pointed out of the page. And you want to, when you represent the magnitude of the magnetic field, you're going to use it's going to have an answer in terms of mu naught I and D. So let's do A together, and then I want you to try B, C, and D by yourself. Okay? So let's go ahead and establish the magnitude of the magnetic field at A due to, well, actually the direction of the magnetic field at A due to the 3I wire. So I'm going to point my thumb into the page, and when I do that, I'm going to make a circle around this, imaginary circle, and my thumb pointed, my fingers seem to be pointed clockwise, and since this is above it, this magnetic field due to the 3I wire is going to be pointed directly to the right. So I'm going to call that, so the x direction is going to be to the right, the positive y direction is going to be up, out of the page is going to be positive z direction. Okay? All right. So that's my coordinate system, that's my magnetic field pointed in the positive x direction. Well, the 2I wire is going to cause a huge circle around it as well, and my thumb is going to be pointed out of the page, and so right above it, when I curl my fingers around, it looks like this one, the 2I wire, is, since it's so far away, its magnitude is going to be smaller, and it's going to be pointed in the negative x direction. Okay, and I subscripted it, negative B2I and positive B3I for that. Okay, well, now we need to sum the magnetic fields at point A, and that's going to be equal to the 3I wire's magnetic field and also the 2I wire's magnetic field, but that's pointed opposite the direction. That's why we have a negative there. It's pointing the negative X direction. The 3I wire's magnetic field is pointing the positive X direction. Okay. Well, if you remember, the equation for a magnetic a magnetic field around a current carrying wire is going to be mu naught over 2 pi, and it's a distance d away, right? I'm doing the 3I wire's magnetic field. It's a distance d away, and that is going to be times 3I. And it's going to be a positive X direction. And again, we're supposed to we'll put the positive out in front of the absolute value. And this is a distance d. The 2I wire has also a magnetic field, but that's a 2I, and that's a distance how many d's away? Well, it's going to be 2 pi times a distance 1, 2, 3 d's from that. Okay. I'm going to actually do something real quick. I'm going to clean this up so it's looks a little bit more. This is 1d away. So that's 2 pi times 1d. And this is 2 pi times 3d. So I'm going to factor out a mu naught I 2 pi d to the front. And what I would get is 3 over 1, which is just 3, minus 2 over 3. The 2 pi is out in front, so minus 2/3. Right? Well, that is just going to be 3 minus 2/3, which is going to be 2 and a third. So this is going to work out to be 2 and a third times mu naught I 2 pi d. And there you go. That's how to do part A. What I want you to do is I want you to try out part B. I want you to do B, C, and D. Okay, so try to do all those by yourself. Okay? All right, let's do B. Let's do the B field here at part B. Well, the 3I current is going to be creating, pointing my thumb into the page, it's going to be creating a magnetic field to the left. I'm going to draw a longer magnetic field. It should be the same size as this one up here, but it'll just be to the left. And since it's also 1d away, but this guy is only 2I, I'm thinking it's going to be not quite as long as this one is to the left, but it's going to be pointed in the rightward direction. So it'll be this. So it'll be plus B2I. So now when I sum the B field at part B, what I should get is, and maybe I'm going to give myself a little bit of room. So I'm going to do it right up here. I'm going to sum the B field at part B. What I'm going to get is, I'm going to get a negative B field due to 3I wire to the right, and to the left, plus the B field due to the 2I wire to the right. And this is what this is going to work out to be, is going to be a negative mu naught 3I over 2 pi d, pointing to the left, plus mu naught 2I over 2 pi d to the right, which is actually going to work out to be, well, I'll just tell you what it works out to be. This is going to be negative It'll just be negative mu naught I over 2 pi d, right? You have negative 3I plus 2I, and they're both d's apart, so all that stuff will just factor out, and you just get this. Let's do C. D's, we're going to save D. We're going to need a larger area because you have to do D in 2 dimensions. So C, let's do C. Try it here. I'm going to establish the directions. So pointing my thumb out of the page, I'm going to get a rightward pointed magnetic field. Oh, you know what? I made a mistake. Whoops. Oh my goodness. I can't believe I made that mistake. Oh goodness. This should be pointed to the left. Oh my goodness. I can't believe I did that. Well, I'm glad I made that mistake. I'm going to keep this in the video. I love it when I make mistakes. When I point my thumb out of the page above it, this guy should be pointed in the negative direction, which means this should be negative, which means, wow, I can't believe I did that. That's fantastic. I'm going to keep that in there. So this should also be negative. So what I realized by drawing this, if this is pointed to the right, it has to be pointed to the left above the 2I wire. So these two magnetic fields should be pointed in the same direction, correct? And so what we're going to have is we're going to have negative mu 3I minus mu 2I, which is going to be negative 5 mu I over 2 pi d. They should have been additive because they were both pointed in the same direction. I made a mistake applying the right-hand rule for the 2I wire. I'm correct on the 3I wire, though. Okay. Anywho, let's go back to this. So the 2I wire should be pointed to the right. The 3I wire should be pointed to the left. And it's going to be negative, and it should be really small. It's really far away. Oops. And it should be a small guy. And so this is negative B3I pointed to the left. So now these guys are going to be subtractive. They're going to be fighting each other. So the magnetic field at C, when we sum that up, that's going to be negative B3I. Remember to put my vector heads on stuff. Even though my handwriting isn't great, I could still be precise as far as my math. So anyways, they're subtractive. The 2I wire's magnetic field is going to be pointed to the right. The 3I wire is pointed to the left. Okay, and that means we're going to get a negative mu naught, and that's going to be 3I over that should be 3I over 2 pi, and how many d's away is it? 1, 2, 3 d's away. So these two are probably going to cancel each other out. The 2i's magnetic field is going to be mu naught, and it's going to be 2i, and that's only 1 d away over 2 pi d. So those 3 i's cancel out, so this is going to work out to be, so you got 2 minus 1, so this is going to be positive mu naught I over 2 pi d. and it's in the positive x direction. All right. Now, D is going to be a little bit of a finesse. So you have to think about this. It's going to have an x and y direction to it, okay? So it's going to have two simultaneous vectors, okay? So this in the 2i direction, this guy is going to be pointing my thumb out of the page towards my face, and this is going to be creating a magnetic field that is going to be pointed in the positive y direction. So I'm going to draw this. I'm going to use different colors now, because if I don't, I'm going to lose count. So this guy here, I'm going to give it red. And that 2i guy is going to be pointed directly in the positive y direction. This A guy, right, this A is going to be, we're going to have to be careful, because this A guy is making a big circle, okay, big circle, and I'm going to actually create a magnetic field in two components, right? So this circle, so this wire right here, this 3i wire, this 3i wire is going to be blue, and it's into the page, and that means over here it's going to actually be pointed down to the left. So it's actually going to have components in the x direction, but also components in the y direction. So it's going to be pointed opposite the direction of the 2i wire in the y direction, but it's also going to have a component in the x direction as well. Okay? So we have to take that into account. So let's go ahead and try it. Okay. Well, let's sum the B field at point D in the y direction. Okay. So that's going to be equal to a positive B2i minus B3i. So the 2i wire, okay, is simple. It's going to be mu naught, and that's a 2i wire, and it looks like it is 2d's away, so that's going to be 2 pi times 2d, right? But the 3i wire is going to be pointed, is going to be a distance that is actually going to be, and I'm going to try to use a color that's associated with this. This distance to here is what we need to use, okay? Okay, and that guy is going to be that distance from here to here is going to be the distance, looks like a distance 2d up and 2d to the right. So that distance r is going to be equal to the square root of 2d squared plus 2d squared. So that's going to be 4d squared plus 4d squared. So that looks like r is going to be equal to d squared, which is going to be d outside, 2 square root of 2. So this is going to actually be 2d square root of 2. And we're going to go back to black for that distance, for that magnitude. So that's its component in the y direction. Okay? And I forgot, we got to go ahead and add like a little angle to this. So we'll add the angle here, right? We'll add the angle here, which is theta, right? Which it's going to be 45 degrees, and this is going to end up being cosine of 45 degrees, right? If this is 45 degrees, 45 degrees, okay. Actually, that should be sine of 45 degrees if that's our angle, because that's attached to that. So if that's our angle theta, then this is going to be, this will be our angle up here. This will end up being 45 degrees. This will end up being 45 degrees, right? So what we could say is the y direction stuff right here, which is going to be off at an angle of 45 degrees. And if that's theta right there, then we'll just call that sine of 45 degrees, which is equal to the cosine part too. In the y direction, in the x direction, at D for this object, only the negative b 3i component is pointed in that direction. And so that's going to end up working out to be the same exact part here, 2 pi, and just to be sure, I'm going to use this as 2d square root of 2 and this will be the cosine component, 45 degrees. And that'll be that part. So since this B3I is pointing off at an angle of theta to that horizontal, it's going to have two components, both in the x and y direction. And you have to take into account that vector direction. And how I got the angle 45 degrees here, well, this is 2D and this is 2D. Well, that means this is 45, this is 45, and so that has to be 45. It really doesn't matter. Okay? So that's how you do a wire in 2 dimensions and 1 dimension. You have to take into account that this really does, and I don't know if I might have misspoke earlier, but this really does have, you have to take into account that there is going to be an angle to this. Okay, so it's typically it's a dot product, okay, which we'll do in Ampere's law. We just went through how to calculate this, but typically you don't do things in 2 dimensions for magnetic field wires, magnetic fields due to current carrying wires. So here's an example from Knight's textbook. You have a 1 meter long wire. It's a 1 millimeter diameter nichrome heater wire. So this is a more complicated problem. It says, what's the magnetic field strength 1 centimeter away from the wire? So you have a wire that's got a length, okay, and it's got a length of 1 meter, right? And its diameter, which is going to be 2r across, is going to be 1 millimeters, which is 0.001 meters. Okay, and we want to know what the magnetic field is. A distance 0.1 meters away. So this is D. Okay, and you're given a 12-volt battery supply. So you're given some hints, right? And first of all, since you're given voltage and you have to give a resistance, your first thing is going to be tasked is defining current. Well, current is equal to voltage divided by resistance, right? And voltage is supplied, but you have to find resistance. Well, resistance is equal to, and I think they did say it's nichrome, so it's a nichrome heater wire. So that's going to account for the density, and so resistance of a wire is actually equal to the area of that wire, that total area, and then you've got the density of that wire, which is density of nichrome, and the length of that wire. So this whole thing is the resistance, the resistivity of that wire. So the density is going to be due to nichrome, right? And then you have to multiply it by the length of the wire and divide it by the area of that wire, right? So that surface area of this plate, right? So that area of that plate, right? The thickness, right? So that's going to be the pi r squared part. And that's how they got the current for this. All right. And then what they did is they just went through what we did. You go mu naught I over 2 pi d. And so in this case, if let's assume the current is going to be pointed out of the page. If the current is pointed out of the page, then this guy was just to the right of that guy is going to be pointed straight up. And so the B field should be pointed straight up. And so in the drawing that we just did, I'll repeat it here. Here's that surface area. That's the wire's surface area. Here's the length of the wire. Here's our distance. Here's our data point. If that current is going to be pointed out of the page, okay, so the current is pointed out of the page, so the B field is going to be pointed up, and this is that distance, which is distance D. So that's how they went through calculating this. So I hope you learned a lot from going through this. What I want you to do is I want you to go ahead and do the lecture tutorials and practice what we've just learned. But I also want you to go ahead and do the readings too, and then start your homework. Okay? Thank you.